Up until now, we've studied methods of integration individually, and the problems we talked about in each lecture were related to a method that we'd studied in that lecture. In lecture 13, we're going to try to put all of the methods together and think about the problem of deciding which method to use when faced with an integral. We'll give some pointers on making the decision, but obviously experience is the best teacher. There are no hard and fast rules. Sometimes 2 or 3 methods work, and you're encouraged to test yourself on the problems given in the lecture and in the homeworks in the book, just to gain that experience with deciding which method to use. First of all, you should be familiar with a lot of the formulas on this table. Certainly the integral of x to the n is something we saw in Calculus 1 when n is not equal to minus 1, and we filled in the missing part in Calculus 2. We know the integral of 1 over x is the natural log of the absolute value of x. Should be familiar with the integral of e to the x, and if you don't want to memorize the formula for the integral of a to the x, you should know how to convert this to a problem about the integral of e to the x. You should certainly be familiar with the integral of the basic trigonometric functions: sine, cosine, secant squared, secant times tangent, secant, and tangent. We haven't studied their co-functions in depth, but the integration formulas are derived in a very similar manner. We haven't studied these two formulas, 15 and 16. They relate to the hyperbolic cosine and the hyperbolic sine, but if you look up the definitions of those functions, you'll see that these two formulas are fairly trivial. Number 17. You should certainly be familiar with this integral when a is 1, that the integral of 1 over 1 plus x squared is tan inverse x. Whether you memorize the formula for general a or not is up to you. You can certainly derive it using trigonometric substitution, but you should certainly be familiar with what the outcome should look like. And again, the same goes for formula 18, the integral of 1 over the square root of 1 minus x squared. You should know that that is sine inverse of x. And whether you want to memorize the formula for general a or not is up to you. Again, you can derive it using trig substitution, but you should have some general idea in your head of what the answer should look like. Number 19, we derived this formula in a particular case in class when a was 5, and the general formula is derived in the same way using partial fractions. And again, there isn't really any need to memorize this formula or memorize all of the details, but you should have a general idea of what the answer should turn out to look like. Number 20 can be derived using the method of trigonometric substitution, and again, it's no harm to keep in mind what the general solution should look like. So faced with an integral, there are no hard and fast rules about what to do, and you basically have to use a problem-solving approach to find the right method. And in fact, sometimes we really don't have a method to solve an integral, and we'll see in the next section that there are many numerical methods for estimating the value of an integral when we don't actually have a method to apply. The first thing is, if nothing jumps out at you, it might just help to simplify the function. So for example, if you're asked to integrate cotangent of x, there's nothing obvious to do, but if you rewrite the function as cosine over sine, it becomes fairly obvious that the substitution u equals sine of x will work. You'll end up with the integral of 1 over u du, which is the natural log of the absolute value of u. Obviously, substitution, if it works, is the way to go, a simple substitution, and you should always check if a simple substitution will work first. Here, for example, this looks like a rather complicated integral, but the substitution u equals ln of x actually reduces it to a very simple problem, the integral of 1 over u to the 10 du. If the integral looks anything like one of these three, then we have some standard methods from that section on trigonometric functions. Some are simple substitutions, some depend on formulas from trigonometry. Most of those formulas that you need will be given on the last page of your exam. And again, if it looks anything like one of these three, you should use one of the methods from that section on trigonometric functions. If you're faced with a rational function, then obviously the method of partial fractions will work. However, you need to be a little bit careful because sometimes the method of substitution, a simple substitution, will work, and it's overkill to apply the method of partial fractions. Integration by parts might work. You should certainly keep that on your checklist, and you should certainly be familiar with the most common examples where integration by parts works and the tricks involved. For example, letting dv equal dx and applying integration by parts twice, and of course recurring integrals. If the integral contains an expression that looks like this, then certainly trigonometric substitution is something to try, but obviously sometimes ordinary substitution works, so you should certainly try that first. And if that doesn't work, certainly trigonometric substitution is a likely candidate. If your integral contains something like this, the nth root of some function, then sometimes you can convert to a rational function by making the substitution u equals the nth root of g of x. And we studied this when we studied rationalizing substitutions. And you may be able to manipulate the integrand to change its form. For example, as we did when we were integrating secant of x, we multiplied by secant of x plus tangent of x over secant of x plus tangent of x, that the substitution u equals secant of x plus tangent of x worked, and we ended up with the integral of 1 over u du. And again, the integral may vaguely resemble something you've already seen. For example, here, this vaguely resembles the integral of u e to the u, except we have this spare cosine here. So we may have to do this integral in two steps. So first we try the substitution u equals sine of x, and we have du is cosine x dx, and then we end up with the integral of u times e to the u du, which of course we can use integration by parts for. So the moral of that story is that your solution may involve several steps and more than one method. Again, experience is the best teacher here, so you should test yourself on integrals from your lecture notes and from the homeworks in the book, and just test to see if you can figure out which method to approach the integral with.